Hello, everyone. My name is Angus. I'll be presenting the paper Real-Time Video Anonymization in Smart City Intersections. So just a brief outline. We'll go through an introduction, including details on the Cosmos project and the intersection that this pipeline was designed for. We'll talk about privacy concerns in smart city intersections, including the problem statement. We'll look at use cases for real-time video feeds and intersections, and some examples of compromised privacy. We'll look at the methodology, so the dataset collection and annotation, the model selection and training, and some inference optimizations. And we'll look at some output videos of the pipeline. Then we'll go into the evaluation of the results. So the accuracy evaluations and the throughput analysis for the inference optimizations. And then finally, we'll go through a conclusion, including a final evaluation of the risk and some limitations and suggested improvements. So the Cosmos Research Testbed, the acronym is kind of a stretch, but you can see where it kind of comes from. The pilot site for this, the Cosmos project, is at 120th Street and Amsterdam Avenue in New York City. And the purpose of this testbed is for advanced wireless technology development. So this includes sensing in the form of high resolution video, high bandwidth communication, and then some edge computing clusters with scalable CPU and GPU resources. So why do we need real-time video feeds in smart city intersections? Real-time video feeds provide high bandwidth data streams for a whole series of applications that are built upon object detection and tracking. So some examples include traffic analytics. So where you're counting vehicles that are passing through the intersection to get an idea of the pattern of traffic. We have communication and feedback with cloud-connected vehicles. So knowing where the vehicles are in the intersection and then broadcasting that information to intersection participants. We have social distancing analysis, so we can localize pedestrians and analyze how far away from each other they are, so to see if they're following social distancing guidelines. And then also there's the radar screen. So now we're going to look at some privacy concerns in smart city intersections. So when you're using ground floor camera feeds, a concern is that the faces of people and the license plates of pedestrians are exposed in those feeds. So this is something that we need to address. So we'll just look at some examples. So you can see in this picture, there's a license plate exposed on the car and the face of this person with the umbrella. So these are things we need to eliminate from the video feed to facilitate downstream applications. So it's just some examples. Another license plate. This face is clearly visible, so that's not good. Another one. So this information in the frames needs to be obscured. Our goal is to build a pipeline for anonymization of faces and license plates in the intersection. So on the right, again, it's the same example, but now the license plate and the face are blurred. So this would be the output of our anonymization pipeline. So just the same examples again as anonymized. This slide kind of just gives an overview of the deep learning-based anonymization pipeline. So the first step is to collect a custom data set from the first floor video feed that we just saw. Next, we chose the YOLO v4 model for its balance of speed and accuracy. And this was trained in the darknet framework. So once we have a trained and accurate model for detecting faces and license plates, then we want to operate this pipeline in real time. So we do some inference optimizations with TensorRT to improve the throughput. In the bottom is a diagram showing the flow of the pipeline. So we start with an intersection video, and we pass this to the YOLO v4 object detector, which outputs bounding boxes of the faces and licenses in a frame. And then we pass those coordinates and the frame into a blurring module that outputs a blurred frame. So this slide just gives some details about the custom intersection data set we collected. So at the Cosmos pilot site, we took 16 different videos of 180 seconds each. And these were recorded at 30 frames per second in 4K resolution. So we took a variety of weather conditions to incorporate all of the different conditions we'd see in real life. So we annotated every sixth frame, and we chose this step to avoid the similarities of objects in consecutive frames. So if you take frames that are too close together, the objects are essentially the same, so there's no variation. So we did every sixth frame, and this amounts to over 14,000 ground truth frames with over 70,000 faces and about 124,000 licenses. Another thing worth noting is that the median object areas, so the bounding box ground truth area of these objects, are very small. So for faces, it's just under 200 pixels, and licenses even smaller at 83 pixels. And this is significantly below the small object threshold for object detection benchmarks like the COCO dataset. I think it's defined at 32 by 32. So this is about 10 times smaller than even that. So these are some examples of frames in different conditions. So this is daytime sunny. You can see that there's shadows from buildings. We have daytime rainy. So the road is wet. The color is a little bit different. Nighttime rainy. And then daytime overcast. So the shadows are different. So the object detector that we chose was YOLO v4. At the time of this work, this was basically the state-of-the-art object detector. And it's a single stage detector. So it's quite accurate, but also the inference time is low. So we want to operate it in real time, so this is important. So I mentioned in the previous slide that the objects we're interested in, the faces and licenses, are small relative to the whole frame. So to accurately detect these, we need to have large input resolutions. So we trained 3 different versions of YOLO v4 based on our data sets. So we chose 608 by 608, 960 by 960, and then 1440 by 1440. This figure is taken from the YOLO v4 paper and kind of just shows the trade-off between accuracy, so mean average precision, and then the frames per second. So we started with the YOLO v4 model that was pre-trained on MS COCO dataset. So this dataset is just, it's common objects in context. So it has 80 classes of objects that are seen pretty regularly in object detection problems. So we fine-tuned YOLO v4 with pre-trained version on our Cosmos dataset, which only has 2 classes, faces and licenses. Our validation strategy for ensuring that the model generalizes well is to leave out 2 out of the 16 videos for validation. We did experiments with segmentation of videos, but we found that identical objects were found in all of the segments. So we got the model to overfit and found that splitting separate videos was a better solution. So yeah, just some details on the training. We used CIOU loss function, drop block regularization, and the batch size was 64. Also, the final weights that we chose were the ones with the highest validation mean average precision. To evaluate the accuracy of our fine-tuned model, we calculated the recall on the validation videos. But we realized that since most of the faces and licenses in our data set are very small and far away, that most of them are already blurred. So on the top right are examples of faces that are less than 250 pixels in area and licenses less than 900 pixels. And these are not really recognizable. And we deduced that you can't really actually extract by the eye any relevant information from them because effectively they're already anonymized. So to exclude these objects from the evaluation, we defined pixel area thresholds at which the face or license is considered not visible. So on the bottom right, we have some distributions of pixel area for faces and licenses. And in the blue, it's the smaller objects, so objects that are not relevant because they are already anonymized by pixelation. And then the orange is relevant objects, so those that are larger than the pixel area threshold. And on the left, we have a plot of recall at the visible object thresholds, at and above, so greater than or equal to the pixel area that we consider visible. And we can see that the recall is quite high. especially for license plates. And then as we increase the input resolution to the models, the recall goes up. So this is an example output of the pipeline. So it's just the anonymized version of a ground floor video. So you can see that the faces and the licenses of the cars are effectively anonymized. And specifically for the faces that are close to the camera, these are the most visible and relevant faces to blur. It works quite well. So these plots show the face recall as a function of the object pixel area threshold. So in these plots, as we move from left to right, we're considering only larger and larger objects. And the green is the true positives, the red is the false negatives. And so you can see that as we consider larger objects, the recall is better. And an important thing to note here is that for highly visible faces, so the ones that are big, the recall is nearly 1. So it does a very good job detecting them, detecting the relevant objects. This is the same plot for the license class. And we see actually that the recall is almost 1 for every model. And this kind of indicates that the license plate detection is an easier task than the face detection. And we think this is because the distribution in terms of where faces are located is kind of random. And the licenses are always in more predictable places because they can't really leave the road, but pedestrians can walk all over the intersection. But again, as we consider only more and more visible licenses, the recall goes up. In order to validate the results of the programmatic accuracy evaluation, we did a manual pipeline validation. And we did this because the ground truth labels are actually very hard to come by and they're super labor intensive to create. So we have to prioritize them for the training. So the process of the manual evaluation is that we process a video through the pipeline to obtain the anonymized version, and then we visually inspect whether or not, frame by frame, if we're missing faces from the anonymization. And these areas you can see on the left and right, indicated by the green and purple lines, are the areas where we consider the faces and licenses to be big enough to be recognized. So this roughly corresponds to the pixel area thresholds we defined for the programmatic evaluation, but it's just not practical to count the pixels for every object in every frame. So we just look and see in these areas if there are licenses or faces that did not get blurred. So the results of the manual validation are largely the same as the programmatic. So this kind of confirms that the anonymization pipeline generalizes well to new intersection scenes. We also wanted to run this anonymization pipeline in real time. So having a model that is accurate is only half of the work. We also need to have it so that the end-to-end latency of this pipeline is under 33 milliseconds. And this number comes from the 30 frames per second. So the 30 frames per second that the cameras operate at, so we don't introduce any additional latency into the sensing. So this 33 millisecond end-to-end latency includes frame read, pre-processing, inference, NMS, and post-processing, the anonymization module, and frame write. To analyze the bottleneck of the pipeline, we did some profiling. So this pie chart shows the time profile of an average pass through the pipeline. So you can see that the inference or PyTorch detect object actually comprises over or almost 3/4 of the. To meet the real-time operating threshold of 33 milliseconds end to end, we need to do some inference optimization. So to do that, we use TensorRT, which is an inference optimization framework for deep learning models, specifically on NVIDIA GPUs. And some of the optimizations that are done with TensorRT are FP16 quantization, layer and tensor concatenation, tuned GPU kernel selection, and dynamic tensor memory. This diagram shows how we use TensorRT with the anonymization pipeline. So there's 2 stages, the serialization phase and then the deserialization phase. The serialization phase is slow, This is where the offline optimization calculations are performed. And then the result of this is a TensorRT engine. And then this TensorRT engine is read into memory in the deserialization phase. And this is where the inference is performed. This slide shows a comparison between the TensorRT optimized pipeline and the non-optimized PyTorch version of the pipeline. So in orange, we have the PyTorch pipeline, and in blue is TensorRT. So in this figure, the y-axis is the time in milliseconds spent at a particular phase of the pipeline. So the most relevant phase here is the inference. So you can see that the TensorRT pipeline is about half the time spent on inference as the PyTorch. So this is good. And this comparison is done with the exact same configurations for both pipelines. So we did the 960 model, batch size of 1, FP32 precision, and then both of these were running on an A100 GPU. So the TensorRT pipeline reduces the inference bottleneck significantly, which was the main step we needed to achieve the real-time performance. So in conclusion, the blurring pipeline is able to anonymize up to 99% of faces and license plates in a given intersection. The recall is high, but there are edge cases where it consistently fails. And these can only be resolved because of the supervised nature of our solution via more training data or possibly with data augmentation based around the edge cases that we highlighted. The blurring pipeline is also able to operate in real time. This is our second goal. So via TensorRT inference optimizations, use of data center GPUs, and reduced precision calculations, we're able to increase the throughput to a point at which the pipeline can be used in real time. Okay, that's it. Thank you all.